All right, guys, let's look at Hess's law. Let me pull up the PowerPoint. All right, so this is starting with slide 41 in on your PowerPoint. Okay. So today in class, assuming you were in class or in the previous part of this lecture, part 4 or 5, I don't remember. I don't know what we're on. We talked about enthalpy being an extensive physical property. So we said that that depends on the amount present. It also is for the reaction written as is or in the forward direction, if that makes sense. So if I were to change an equation, okay, there's two different changes I would make. I might want to multiply it by some factor to give me a different mole-to-mole ratio. Okay, so that's what this first example is here. I have solid carbon plus molecular oxygen gives me CO2. Okay, I have 1 mole of each, and then they have determined using the delta H of formation that this reaction gives off negative 393.5 kilojoules of heat. Well, if I instead wanted the amount of heat given off per every 2 moles of reactants and products, I would multiply this equation through by 2. If I do that, then I also have to multiply my delta H by 2. Okay, so whatever you do to the reaction, you also have to do to your delta H. Okay, one other thing you could do is we could reverse the reaction. So if you reverse the reaction, your original products now become reactants and vice versa. So that changes the sign of your delta H. Okay, so if you reverse a reaction, you change the sign on your delta H. Okay, so we're going to need these rules, I guess we'll call them, to deal with Hess's law. Hess's law states that the change in enthalpy for a stepwise process is the sum of your enthalpy changes. In other words, if I have 2 reactions, we'll call them reaction 1 and reaction 2. I add them together to get a reaction 3. Then my delta H for that reaction 3 is simply the sum of the delta H for reaction 1 plus plus delta H of reaction 2. Sorry, you simply add them together. Okay, so that's easy, right? But sometimes you're going to have to manipulate equations to get them how you want them so that when you add 2 reactions together, it gives you the actual desired reaction. Okay, so let me show you what I mean. If you look at example 9.9, I want to find the delta H of reaction for 3 moles of solid carbon plus 4 moles of H2, yielding 1 mole of propane, C3H8. All right, I'm not giving you any delta H of formation, so you can't find it that way. Instead, you've got to use these 3 equations I've given you that already have delta H's associated with them, okay? So we've got to manipulate these 3 equations so that I can add them together to give me this equation up top. All right, well, if we look at the first equation, I see that I have C3H8, but it is a product. I mean, it's a reactant. I want it as a product. Okay, so the first thing I'm going to do is I'm going to reverse that very top equation. So it becomes 3CO2 plus 4H2O yields C3H8 plus 5O2. Okay, so since I reversed it, I have to change the sign on my delta H. I'm going to write it right here. So it becomes positive 2,043 kilojoules. All right. Okay, so that is the only thing in this reaction that I need for this top reaction. Okay, so let's look at the next reaction. I have carbon as a reactant. Nothing else in that equation matters to me. All right, so in that reaction, I have 1 mole of carbon. Up here, I want 3 moles. So I'm going to take that equation as it's written, but I'm going to multiply through by 3. So I'm going to do the exact same thing to its delta H. So it becomes 3 carbons plus 3 oxygens plus 3 carbon dioxides. Then my delta H will be 3 times negative 3 times 393.5. That delta H is negative 1,180.5 kilojoules of heat. Okay. Looking at these two equations so far, if I were to add them together, if I have a reactant that is a product in another equation, it cancels out. For example, this 3CO2 right here will cancel out right here because they're on opposite sides of the equation. The opposite is true. So these 3 O2s will cancel 3 of these 5. So here I'm just left with 2. Okay, so that's what we've gotten so far. All right, let's look at the third equation. Third equation, I need that H2 and I need it as a reactant, but I need 2 of them. So for this equation, I need to multiply it by 2. So I'm also going to multiply its delta H. So 4 H2s, 2 O2s, yields 4 H2Os. And then my delta H for that reaction then will be 2 times negative 483.6. So you get negative 967.2 kilojoules. All right, so I'm going to add these 3 equations up. You'll notice that this 2H2O, right? I mean, this 2O2 is going to cancel that remaining 2O2 in the very first equation, and then these 4 water cancel these 4 water. So now I bring down everything I have left. And what do you know? It is the exact equation from up top. So all I need to do now is add these 3 delta H's together. So let's see, plus heat plus 43. Right, so I got my delta H to be negative 1.47 kilojoules. Okay, pretty simple. So it will always work out like this. Your equations that you're given to manipulate will always, in some way, cancel out to be your desired equation. And all you'll ever have to do is either reverse it or multiply it by some coefficient. All right, I think, let me erase all this because I left this part up here too. So if you need to read that in words, I left that on the slide for you. Okay. It keeps going. So here's another example I'll work through with you real quick. So again, I'm looking for the delta H of this top reaction. So this is what I'm going to compare everything to. Right here. Okay, so let's look at our equations. The first one, NO2, NO2. So I need to flip this first equation. I'm not going to mess with this just yet. The reason I'm not is because this is 2, this is 3. You can't multiply that by any whole number to get what we're interested in. So let's just leave it and hope it works itself out. Okay, so let's reverse it. NO plus O2. So then my delta H, I'm just reversing the sign. It's going to be positive 113.1 kilojoules. Okay, moving to the next equation. I don't need this or this. I do need this. Would only need one more. So what do I want to do? Looks like I'm going to have to half one of these equations. NO2 is going to be there, but we only want one. It looks like we should have this first one. I really love when we're dealing with fractions. Why did they do this? All right, so I actually need to half this. I don't like this example because we didn't talk about this. Let me see. Is there an D? Let's do this bottom one instead. All right, let me do this real quick. Let me delete. I'm going to delete this top stuff. And we're going to do the bottom one instead. I don't like this example right here. These arrows don't ever move like they're supposed to. All right, let's do this example. I'll show y'all how to do the one that I just deleted, but I'd rather do that in person because we need to talk a little more about it. Okay, so let's look at this one. All right, we're trying to find the delta H for this equation. Oh my gosh. Are you kidding me? All right, that's gonna go that way, but you've got to half it again. So the problem is they didn't tell you all you needed to know. Trying to see. Oh, they're telling us to just multiply it by half then. All right, then yeah, we'll do it. Okay, we are going to have to multiply them by fractions. I know, how lovely of them. So in this first one, I'm interested in this and this, but I have 3 here and only 2 in this reaction. So I say we multiply it by 3/2. Gas, gas, gas. And our delta H also by 3/2. Okay, if I divide it by 3/2, this 2 cancels. This 2 cancels, so I'm left with 3 H2 plus 3/2 O2 yields 3 H2Os. Let's go ahead and 3 divided by 2 times negative 483.6. So my delta H becomes negative 725.4 kilojoules. Okay, now we can deal with that next equation. Looks like in the next equation, we need to multiply it by 1/2. So let's multiply this one by 1/2. I see that because I have 2, I only want 1. So that's the only way I can get rid of that 2 is to multiply it by 1/2. So it becomes 3/2. Oh, wait, we've also got to reverse it. So O3 yields 3/2 O2. So then our delta H, multiply it by 1/2, but you also got to change the sign. So multiply 1/2 times the negative of what you see there. There's one delta H, there's the other. All right, so then my 3/2 O2 cancels. I can bring everything else down. Okay, so then I have the equation I want from up top. Now let's add my two delta H's together that I have circled. And we get delta H equals negative 8.1 kilojoules. Sorry, I was not expecting us to have to multiply by fractions this early. I thought they'd give us a few more examples where we can multiply by whole numbers, but that's okay. So for your pre-lab, for experiment 11, I think it is, I don't believe that you have to use fractions, okay? I think it's pretty straightforward. Whole numbers, you multiply by whole numbers or you simply reverse it. But I'll get us a few more examples of Hess's law to practice with, but I just wanted to go ahead and do this for those of you that kind of maybe wanted to work on your pre-lab over the weekend. All right, so I've pretty much lectured on everything I want to talk about in chapter 9. So the next part, or the next time you come to class, all we're going to do is work problems, work a few more examples from each type of problem. Okay? All right, have a good weekend.